Okay, so again, here in this video, we're continuing our applications of Newton's laws, and we're going to talk about free body diagrams and problem solving. So you saw a little bit of free body diagram in the last video when I was drawing arrows on the pictures, but let's formalize what is a free body diagram. So what the free body diagram really does is allows us to find what is called the net force, which is, again, is just simply the vector sum of all the forces acting on an object. So the vector sum could be, basically you're going to split up in the horizontal, vertical directions. You may have to end up finding a net force based on how much force is going one way versus how much force is going, how much force is going vertical versus how much is going to horizontal. So when it comes down to the end, the problem solving is very simple. It's just broken down into 3 words. Okay. And those 3 words are draw, sum, solve. Okay. And so the first step is draw, which means you draw the free body diagram, or FBD. Again, it's just a picture or a pictorial representation showing on the object, showing all the forces acting on it. So here's just a quick example with a free body diagram. So we have this hockey puck sliding at constant velocity. Which sketches below is the correct free body diagram for the puck at this current situation, right? And so it's going to be, this one is going to be our answer for part A, because again, if the object is sliding, there's no other force acting on it, right? So that just means that there's no push force when we slide. Okay, and so we should have no force that is going horizontal, even though it seems weird that the motion is horizontal, but there's no horizontal force, right? Again, because dynamics is a study of, we don't, like, it started, we don't, this is in its motion, right? It's not at the beginning or at the end of its motion. Okay, what would be your answer if the puck was beginning to slow down? So what we would need to do is we need to accelerate in the negative direction. So we would need a force pointing in the opposite direction of motion. And you can see that here with sketch C, because this force, and we'll later define what that force is, but you can see the motion is going to the right, but this force here is acting against it, which means now the object is going to slow down. But what you could see here is, the arrows on this puck. In fact, you don't even have to draw the puck. You can just draw a box or a dot to show that. Okay, and the next 2 words are going to be sum and solve, right? So sum means to actually do that vector sum in the horizontal and vertical directions, and you're going to set it equal to either 0 or m times a, right? 0 is m times a, where your acceleration is equal to 0. So technically you are setting it equal to m times a, even if it is equal to 0. And then you're going to solve for the problem, or solve for what you're looking for. Most of the time you can be looking for acceleration, but in other problems you could be determining, let's say if it's a friction problem, it could be the coefficient of friction. It could be a tension. It could be, in the last in the last video, you saw that we were solving for apparent weight. So it doesn't have to be acceleration. Most of the time, though, it could be acceleration. So let's kind of look at how this is all put together. Okay, so you got a friend. Basically, that friend that gave us the gift in the last video, now they're going to pull that box across at an angle. So then we're going to calculate the acceleration and then the magnitude of the upward force exerted by the table. So we're looking for the normal force. So free body diagram. Again, you can just do a dot or a box, right? But that dot is going to represent the object. So I have an upward force from the table. I have a downward force of gravity. But then I have this pulling force, which they call FP, right? That's at an angle of 30 degrees. And so we're going to have to take care of that, the angle, by using some trig. But if this was the AP test, this is what you'd want to do, right? You don't want to put any extra forces on it, which means any extra components. So I wouldn't want to draw an FPX or FPY, but for the sake of this video, let's do that. So FPX is here. And the good thing you see is that that is the only force that is causing the acceleration, and FPY is here. So that's going to kind of contribute to our normal force, which we did last video. Okay. So first thing is finding the acceleration of the box. And what I like to do is I like to make a T-chart with my horizontal and vertical sides. So I'm going to sum the forces in the x direction. It's not going to be equal to 0. It's going to be equal to m times a. Because easy way to think about it is we are looking for the acceleration. Right? So it's going to be equal to ma. And so the only force is fpx equal to m times a. And a is going to be fpx over mass, but fpx is fp cosine theta. And so we're going to say A equals the pulling force, which was 40, cosine 30 over the mass of the box, which is 10. So you can do just a little bit of canceling if you would like, but we find the acceleration is going to be 3.46 meters per second squared. So one thing you know is that you see how the vertical doesn't affect this, right? Because the only force acting in the x direction is the x component of that pulling force. Now let's look at the y direction. And this is very typical what happens in the y direction if it's on a table, is that the acceleration is going to be 0. Because what we're saying is that box is going to be pulled on the table. We're not pulling it off the table. And so we would have an upward force from Fn, we would have an upward Fpy, and then we have a downward Fg. And so this is what I'm looking for. So Fn equals Fg minus Fpy. And so it's going to be mg minus Fp sine theta. And so it's going to be 10 times 9.8 minus 40 times sine 30. Okay, and then we find that the normal force provided by the table will be 78 newtons. Again, if I want to recap the steps here, right, draw is our free body diagram. This line right here is the summing. And then what you see down here is the solve, right? And so remember, basic strategy, draw, sum, solve. Okay, and really you're going to apply that to all these application problems.